Hi, everybody. So now we're going to continue our discussion of group actions, and we're going to look at I think, two really fundamental things to know about group actions, and that's the idea of the orbit of a point and the stabilizer of a point. These two things work together to really relate the structure of the group to the structure of the set on which the group acts. And they're fairly natural things to think about. So let's start with orbits. So suppose you have a group acting on a set. So G acts on X. So in other words, you can take an element of X and you can move it by an element of G. And we say that 2 points, X and Y, are G equivalent if you can get, let's say X and Y are G equivalent, if you can get from X to Y by an element of G. So if you think about the action of G, here's your X, here's G taking you to GX. If you can get from X, if you can get from X to Y, then X and Y are G equivalent. And this is an equivalence relation. And let's just check that really quickly. So first of all, is X equivalent to X? Yes, because X is the identity times X. So you can always get from X to itself by applying the identity. If X is equivalent to Y, is Y equivalent to X? Well, that might not look, because it's not symmetric, right? X equivalent to Y means that Y is G times X. But if Y is G times X, multiply both sides of this equation by G inverse. And you get G inverse Y equals G inverse GX. But this is the identity times X, which is X. So if X is equivalent to Y, remember the equivalence just means there's some G so that Y is GX. And if there's a G so that Y is GX, there's another G so that X is GY. It just happens to be the inverse. So it's symmetric. And what about transitivity? If X is equivalent to Y and Y is equivalent to Z, then that means that Y is G1X and Z is G2Y. So in my picture here, you can get from X to Y by G1 and from Y to Z by G2. And if you look at this, what you can do is you can go do the whole thing all in one step. Namely, you can do Z is G2 G1X, because G1X is Y and G2Y is Z. So by chaining these together, you can take the direct shortcut G2 G1. So we have an equivalence relation, and as we've done many times in this class, when you have an equivalence relation, what happens is that this means that the set X gets divided up into equivalence classes. And those classes are called orbits. And the way to think of an orbit is each orbit is everything you can get to if you pick an X and then you apply every possible element of G to it. So I like to write orbits as GX like this, but the book tends to write them as O sub X, orbit of X. But I think this helps sort of drive home the point about what an orbit is. It's what you get by picking an element X and considering all the places that G takes you. If you think about S3 and the conjugation action, we know that two permutations are conjugate if and only if they have the same cycle decomposition. And what that's saying is that if you consider the action of S3 on itself, that two things are, so to be conjugate means that sigma is G tau G inverse. And so we know that two permutations, sigma and tau, are conjugate if and only if they have the same cycle decomposition. So that means that the orbits in this particular case correspond to the cycle decompositions. So there's the identity element, there's the two cycles, and there's the 3 cycles in S3. And if you think about how the S3 acts on this, if you conjugate the identity element, you only get the identity element. If you conjugate a transposition, then you only get another transposition, and there are 3 of those. And if you conjugate the 3 cycles, you get the other 3 cycles, and there's really only 1 of those. I mean, there's 2 total. So the orbits under conjugation, not just in S3, but actually in Sn, because we know this result in general, the orbits under conjugation are the conjugacy classes. They're the set of cycles which have the same cycle decomposition. And to say you're in the same orbit is to say that that you're conjugate. To be in the same orbit under the conjugacy action is to say that you're conjugate. So we know you can get from any cycle to any other cycle by conjugation, provided they have the same cycle decomposition, but you can't get from one cycle decomposition to another. The other crucial definition is the idea of a stabilizer. So the orbits are subgroups of X, the set on which you're acting. The stabilizers are subgroups of G. And the way you make a stabilizer is you take an element X in X, and the stabilizer of X is the collection of elements of G which leave X in place. They don't move it. So let's go back to our immediately preceding example. And we know that, let's take the element E in S3. And we're going to have the conjugation action. So what's the stabilizer? Well, the conjugation action says G is in the stabilizer of the identity if and only if G inverse is equal to E. But that's true for any G. So the stabilizer of the identity is all of S3. What about if we look at a transposition? What are the G's in S3 so that G times 1, 2 times G inverse equals 1, 2? Well, this is something we've seen before as well. This says that G times 1, 2 is 1, 2 times G. In other words, G commutes with 1, 2. Now, if G is going to commute with 1, 2, or if it's going to, we know how, what are the possibilities? Well, G could be the identity. The identity commutes with 1, 2. G could be the element 1, 2 itself, which commutes with 1, 2. Could it be anything else? Well, if it's a different transposition, like there are 2 other transpositions, 1, 3 and 2, 3, and we know that 1, 2, 1, 3, 1, 3 is 2, 3, so that does not commute. Or in other words, it doesn't fix 1, 2. And similarly, 2, 3, 1, 2, 2, 3 is 1, 3, which is not the same. So that doesn't fix 1, 2. So there are no other transpositions in there. And there's also no 3 cycles, because if you were to conjugate by the 3 cycles, it's also going to change this. So the stabilizer of this element is just the 2-element subset consisting of the group of the element E and 1, 2. And the other thing we can look at is if G happens to be a 3 cycle, then what commutes with, let's call that X is 1, 2, 3. What commutes with X? Well, G does. I mean, X itself does, and also the other 3 cycle. So it turns out that the things that commute here are E, 1, 2, 3, and 1, 3, 2. So the stabilizer of the element 1, 2, 3 is the rotation group. Now, I sort of took this for granted, but we should probably check that little lemma here that the stabilizer is a subgroup. So remember how it's defined. It's defined to be the collection of G so that Gx equals X. So is the identity in Gx? Yes, because Ex equals X. Is it closed? If G1 and G2 are both in Gx, then G1 times G2x is G1 times X, because G2x is X. So this is G1x. So this is X again, because both G1 and G2 fix X. But that's equal to G1, G2, X. So G1 times G2 also fix X. So it's closed under multiplication. And what about under inverses? Well, if Gx equals X, then we can multiply both sides by G inverse. And then this is X. And so we get that G inverse X equals X. So the set of elements which fix a point in an action is a subgroup. And we saw that up above. The subgroups were respectively the whole group, the group with 2 elements, and the group with 3 elements. Let's look at some more examples of actions and stabilizers, of orbits and stabilizers. So when D4 acts on the square, let's look at what is the orbit? Let's label the vertices 1, 2, 3, 4. So the set of vertices 1, 2, 3, 4 should be partitioned into orbits corresponding to being G similar, G equivalent. But we have this rotation R in D4, and R takes 1 to 2, 2 to 3, 3 to 4, and 4 to 1. And if you look back at the definition of equivalence, that means that 2 is equivalent to 1. 3 is equivalent to 2. 4 is equivalent to 3. And 1 is equivalent to 4. In other words, all the vertices are equivalent, are G equivalent. So there's only one orbit. And it consists of the set 1, 2, 3, 4. What about stabilizers? So what's the stabilizer of the vertex 1? In other words, which symmetries of the square fix this point? Right here. Well, the rotation doesn't, because the rotation moves 1 up to here. The other elements are the reflections around these various axes. And the only one of these reflections which fixes 1 is this one. It interchanges 4 and 2, but it leaves 1 and 3 alone. So the stabilizer of 1 consists of the identity element and also the reflection 2, 4, which fixes 1 and 3. And similarly, the stabilizer of the point 2 consists of the identity and the reflection that goes diagonally this way, that fixes 2, and so that interchanges 1 and 3. And the stabilizer of G3 is the same as the stabilizer that we looked at here. It's the identity and 2, 4. And the stabilizer of G4 is the same as this one here. It's the identity and 1, 3. Those are the stabilizers. There, you notice, so I mean, the reflections through the midpoints of the sides, they don't stabilize any vertices, so they don't occur in any of the stabilizers. Okay, some more examples. S4 acting on itself by conjugation. So this one's a little bit more complicated. So we know that the orbits are the conjugacy classes, and there are the following conjugacy classes: the identity, transpositions, 3 cycles, products of transpositions, and 4 cycles. And we know, because we know that every G in S4 is conjugate to one of these 1, 2, 5 examples. Because, right, we know that if you take an arbitrary G in S4 and you look at its cycle decomposition, it has to have one of these forms. And depending on which form it has, it's going to be conjugate to that element. And that means it's going to be G equivalent to one of these things. So these are representatives for the equivalence classes under G equivalence. And so each of them gives rise to an orbit. So what are the orbits? So the orbit of E is the collection of G, E, G inverse, where G is in S4. But of course, G, E, G inverse is just E. So it's in an orbit all by itself. So the orbit of 1, 2 is the collection of G, 1, 2, G inverse. And that's the collection of things whose cycle decomposition is AB. And how many of those are there? Well, we did this calculation once. Basically, you can choose 2 elements out of the 4. There are 6 ways to choose these 2 elements. And each of those, so there's 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Those are the 6. So this orbit has 6 elements. What about the orbit of 1, 2, 3? Well, this is the collection of 3 cycles in S4. And how many of those are there? Well, we have to leave out one of the 4 elements. So there's 4 ways to do that. And that gives us our 3 elements. But there are 2 different ways to arrange them. So like, for instance, 1, 3, 2 and 1, 2, 3. So there's a total of 8 elements in this orbit. And then we have 1, 2, 3, 4. These are the products of 2 transpositions. There are 3 of these, namely 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. And finally, there's 1, 2, 3, 4, the orbit of that. And the way to think about that is you can pick anything to go first, and then the other 3 is a permutation of 3 things. So there's 6 of those. And if I've done this right, we have 6 and 3 is 9, 9 and 8 is 17, 17 is, and 6 is 23, and 1 is 24. So the orbits of the action of S4 on itself by conjugation are the conjugacy classes. Let's look at a stabilizer just for fun. So what is the stabilizer of the transposition 1, 2? So in other words, which elements have the property that they commute with 1, 2? Well, certainly we know that the identity and also 1, 2 have that property. And it's also the case that 3, 4 has that property, right? Because 3, 4 is disjoint from 1, 2, so it has to commute with 1, 2. And the stabilizer is a subgroup. So if it has 1, 2 and it has 3, 4, it had better have 1, 2, 3, 4 in it. So there's 4 elements in the stabilizer. Am I missing anything? Well, if you have a transposition which has either a 1 or a 2 in it, it's not going to commute with 1, 2. Because we know that, for instance, if you use 2, 3, the effect would be to replace this 2 by a 3, so it wouldn't commute. So we've already accounted for all possible transpositions which commute with it. Namely, they have to be 1, 2, or they have to be disjoint from 1, 2. What about 3 cycles? Could you have a 3 cycle that commutes with 1, 2? Well, any 3 cycle is going to move. It's not going to be disjoint from 1 and 2, because if you have 3 things and there's only 4 total, you're going to have an overlap. And that means you're going to end up changing the 1 and the 2. What about a 4 cycle? Same problem. It's not going to be disjoint from 1 and 2. And we've already accounted for one of these products, 1, 2, 3, 4. What about, but if we had, for instance, 1, 3, and 2, 4, then the effect of that would be to change the 1 to a 3 and the 2 to a 4, and so it wouldn't preserve this. The upshot of this is that this is the full stabilizer of this element. What about, do you want to do one more? The stabilizer of 1, 2, 3. Well, this is the collection of elements G for which G 1, 2, 3, G inverse is 1, 2, 3. And we already know that the identity 1, 2, 3 and 1, 3, 2 are going to commute with this. But the rule is basically, in order to commute with this, you either have to be disjoint from it, or you have to equal one. It have to involve exactly the same letters. So none of the transpositions are going to commute with this. The 4 cycles aren't going to commute with this. And the products of the 2 transpositions aren't going to commute with this, because they're all going to overlap in a way that's going to prevent it. So these are 2 examples of stabilizers. We'll see in a little while that there's some information you can use to make this computation easier, but notice that in each case they are a subgroup. What about the orthogonal group acting on the plane? So remember what the orthogonal group is. It consists of 2 kinds of operations. It has SO2, which are the rotations. And then it has a reflection, such as the one which reverses the y-axis. And in general, you have also any reflection around any line. So what's the orbit of a point? Let's look at the orbit of the point 1, 0. In other words, the orbit of I. Well, under rotation, we can move this point all the way around in a circle. But because this is an orthogonal group, we can't change its length. So any point at distance 1 is going to be in the orbit of 1, 0. And because of reflection doesn't change the length of this vector, points may, within this orbit, there may be some points that get moved around, but it's still the same orbit. So the O of 2 orbit of 1, 0 is the circle, the unit circle. And more generally, if you take the O of 2 orbit of a vector, let's say n0, then when you rotate it around, you're going to get the circle of radius n. And then finally, I guess if you apply it to 0, you just get 0. So the orbits are these circles. What's the stabilizer of 1, 0? Well, there can't be a rotation involved, because if there was a rotation, a non-trivial rotation, it wouldn't be 1, 0 anymore. But there is one reflection that preserves it. Namely, you can use this matrix. So the stabilizer of 1, 0 is the identity and 1, 0, 0, minus 1. No other reflection is going to stabilize 1, 0, because any other reflection axis is going to move 1, 0 somewhere else, and any rotation is going to move 1, 0 somewhere else. So the only things which preserve 1, 0 are the identity and this one reflection. And there's nothing special about 1, 0. That would be true. Any other vector is going to have the identity element, and then it's going to have a reflection around the line through it, which would also leave it fixed. Oops. Couple more examples. What about Z acting on R? This is kind of an unusual one. So this is, what is the orbit of 0? Well, it's everything you can get from 0 by adding an integer. In other words, it's the integers sitting inside R. What's the orbit of pi? Well, it's all the integers that you can get by adding, all the numbers you can get by adding an integer to pi. So the orbits are, if here's the real line, and you pick a point, this is 0, let's say, you pick a number, here's your R, and you think about all the shifts, R plus 1, R plus 2, R plus 3, R minus 1, R minus 2. That's the orbit. These points are the orbit of R. What about the stabilizer of R? So the stabilizer of X is the collection of integers n such that X plus n is equal to X. And that's just 0. So the stabilizers of points here are all 0, and the orbits are all the integer translates of a particular real number. And the last one is, what if you take the following thing? So your set X is collections of zeros and ones, like this, and there's n of them. So in other words, if you want to be fancy about it, it's Z2 cross Z2 cross Z2 n times. Or you can think of it as the binary numbers of length n. And we're going to let Sn act on this by permuting the positions. So let's look at a very simple case. If we let n equals 3, then we have 0, 0, we have 8 things down to 1, 1, 1. And if we label the positions 1, 2, 3, and so for instance, the transposition 1, 2 just interchanges the entries. So it would take 0, 0, 0 goes by 1, 2 to 0, 0, 0. 0, 1, 0 goes by 1, 2. You flip the first two positions to 1, 0, 0. 0, 1, 1 would go by 1, 2 to 1, 0, 1. And then just to make it maybe mind-numbingly obvious, if you were to apply 1, 2, 3 to this, then you would send the 0 to 1. You would move the first position to the second position, the second position to the third position, and the third position to the first position. So you would move this 1, you'd cycle the digits around. What are the orbits? Well, if you think about what's going on here, if I give you an arbitrary sequence, so the orbit of an arbitrary sequence, let's say it's 1, 0, 1, 1, 0, 0, 1, 0, 0, 1. I can always find a permutation which moves all the zeros to the beginning and all the ones to the end. So if I call this X, X is always going to be G equivalent to something of the form 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. So two X's are in the same orbit. X is equivalent to Y if and only if they have the same number of ones. So the orbits, there are n orbits. There's the 0, there's the 0, 1, or the one that has 0 ones, the one which has 1, 1. So this is represented by 0, 0, 0. This is represented by 0, 1. 2 ones, this is represented by 1, 1, and so on. Those are the orbits. What's the stabilizer? Well, if you want to, let's take, for example, the stabilizer. Maybe we'll take n equals 5 just for simplicity, and you'll see the answer. So what's the stabilizer of this element? Well, the stabilizer are the permutations which preserve this element. That means you can do anything to these first 3 positions and keep them 0. And you can do anything to these last 2 positions and keep them 1, provided you don't mix up the 2 parts. So these are the permutations here on positions 1, 2, and 3, and these are the permutations here on 4 and 5. And in general, that's the stabilizer. In general, is going to be a product of the stabilizer of, if you have k zeros and n minus k ones, the stabilizer is sk cross sn minus k, where this sk permutes these and this Sn minus k permutes those. Interestingly, if you want to know what is the size of the orbit, how many elements, for example, are in this orbit? Well, that's the question. How many ways can you put 2 ones in n things? And those are the binomial coefficients. Okay. The last thing I want to deal with in this section is a proposition, but I think I'm going to make that into a separate video. So the thing we're going to prove is this relationship between stabilizers and orbits, that the index of the stabilizer is the size of the orbit, and that'll be in the next video.